Assalamualaikum, my name is Muhammad Anif. I'm from group 4, which is our topic is Ammonia Refrigeration Working Principle. Okay, my group members is Muhammad Iqmal, Khairul Haziq, Muhammad Irfan and Izzat Izzuddin. I'm going to present about the problem statement. Refrigeration cycle, also known as reverse Carnot cycle. The problem that can be overcome in this topic is how to improve the coefficient of performance of this cycle, which is COP. Okay, the whole cycle we also must to understand to make sure we can troubleshoot if any abnormal situation occurs. And lastly, the working fluid is one of the factors that can be affect the change of our process. The introduction of a refrigeration cycle, it is an indication process, which is the change of thermodynamic properties of the refrigeration and the energy that transfer between the surrounding area. And it is also known as a reverse Carnot cycle, as I mentioned before. And there are a few phase change during the refrigeration process, which is have four basic components, which is the evaporation, superheating, compression, and condensation.
For the introduction, there are a few processes occur during the refrigerant cycle, which is first is evaporation, superheating, compression, condensation, and throttling and expansion. First, at evaporator, go to the compressor. The phase is saturated vapor and the temperature and pressure is low pressure. Next, from compressor, go to the condenser. It is a high pressure and in superheated vapor. Temperature also high because there are Q in here. Next, third is condenser, go to the expansion valve. The phase is saturated liquid. The pressure still high, but the temperature is slowly down. And the next is from expansion, go smaller to the evaporator. The phase is liquid and vapor and the pressure and temperature also low. For this background of study, we want to study about the process of refrigerant cycle. There are four processes occur in refrigerant cycle. For the first is isothermal process at stage 4 to 1. The temperature is constant at this stage. Next, the process is isentropic compression process at stage 1 to 2, which is there are Q in here because of the compressor compress the working fluid here. Then we go to the next step is isothermal process, which is temperature 2 and 3 is constant also. And lastly is the isentropic expansion at stage 4 to 1, which is the pressure drop drastically because of expansion valve.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan Grossly and I would like to continue my part, which is the objective. So for our objective, firstly, to understand the concept of the refrigerant cycle. The second is related refrigerant cycle with process in industry related. And the third is gain knowledge on the theoretical and calculation. So we go through the equation related. For the equation related, firstly, heat supply plus the heat rejected equals to net work done, which is, by example, Q1 equals to Q2 minus W, or Q2 equals to Q1 plus W. The next, the heat extracted from the source at the temperature TR1 by the working substance. For example, the refrigerating effect working substance is Q1 equals to TR1 S1 minus S2. So next, for the heat rejected to the heat sink at the temperature TR2 can be calculated as Q2 equals to minus TR2 S3 minus S2 equals to TR2 S2 equals to S3. And lastly, where S2, S3 entropy at state point 2 and 3 respectively. And at the process 1, 2, S1 equals to S2. And as a tropic process 3 to 4, S3 equals to S4.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqmal. I will explain about the application working process of the ammonia. So starting of this process is the compressor give the high pressure vapor to the condenser. After that, the condenser give to the receiver and make the high pressure liquid. So it will flow to the expansion valve and liquid separator, and the pump sucking up the liquid to the evaporator, and the evaporator make the vapor mix or liquid and then give to the liquid separator, and the cycle is repeated.
Okay, for this question, we have to find first the refrigerant effects, 2 the work input to the compressor, 3 the coefficient of performance of this refrigerant cycle, and 4 the mass flow rate of the refrigerant. The detailed calculation shown in the report after we follow the step by step, and we got the answer without subcooling 337.8 horsepower, and we got the answer with subcooling 330.2 horsepower. Okay, for the next slide is a discussion. We refer from our calculation. The first one is subcooling. It's condensed liquid refrigerant, and it's usually subcooled to a temperature lower from the saturated temperature to the condensing pressure of the refrigerant. And it's also done to increase the refrigerating effect. Okay, for the superheating, the purpose of superheating is to avoid compressor slugging damage. It's also increase the enthalpy, will increase the coefficient of performance COP of a refrigeration cycle.
I will continue with the conclusion. So refrigerant is one of emerging segment in the industrial. So the compressor are the heart of the refrigeration system. So globally, more and more new refrigerant with improved properties are being produced. Lastly, is refrigerants will be generated in the future, which will not only equal but even exceed the efficiency characteristic of today's refrigerant.
For the recommendation on how we want to improve the coefficient of performance, which is COP, in this refrigerant cycle, first thing first, we must set in mind that the enthalpy must be enlarged between stage 4 and stage 1. So the COP will increase. Okay, for the method to increase the COP is such as, first is subcooling and superheating. Next is by multi-stage vapor compression system, and also can perform a cascade system, two-stage compound system with a flash cooler, and also two-stage compound system with vertical intercooler. With this method, the enthalpy will enlarge and the coefficient will increase. There are many benefits if the COP is increased.
That's all from us. Thank you.